Hi, everybody. We'll just hang on for a couple of seconds here. Let everybody join in while I kind of get my stuff organized here on my desktop. You should see my my title slide here. Good morning, everybody. I hope you're having a great Wednesday. And I think this is Wednesday. Yeah. So anyway, let's get busy here, and as people join in, we'll discuss. A little bit different this time since we're live again. We haven't been live in a couple of months now. It's been recorded. If there is anybody that has any questions, feel free to pop them up in the chat. I'll try to have a look and keep track of that at the same time. Have my meeting controls up here, so we should be able to do that. Anyhow. So today, I want to continue on with the topic that we actually started last month, and it's going to progress into. We're talking about transmit receive streams, and so today we're going to talk about Mimo, about how it works, what it is, and you know, from my particular perspective, I'll take you know, some complex algorithms and that. We'll break them down and describe them in English that you know, everybody else can understand. So I'm hoping today that I can take some of the mystery out of the different forms of Mimo that we're dealing with today in our telecom equipment. So the questions we need to ask is, you know, why Mimo? What do we need them for? And what are the characteristics of a Mimo antenna system? What are the types of Mimo, and what are the options? What can we do with Mimo as we are deploying these networks? What are they going to do for me? That's the question that we all have to ask. And so the manufacturers, of course, they all have Mimo in some form today, and so I hope that through this 45 minutes or whatever it is that we're going to spend in the next, that I can take and explain some things, and we can have a look and see what Mimo is. Now, my latest little telecom Bible here, I want to give Bob Heath here a shout out, and this introduction to wireless digital communication is kind of my latest go-to book. He's got a lot of really great stuff in here, but it is written from a mathematical point of view. So I've got just an example down here. This happens to be the formula for one of the types of MIMO called maximal ratio receive combining. So this is the kind of complexity that this book has. It's far from a wireless for dummies book. So if somebody's looking for that, this is not it. But it does very succinctly explain how these processes work, and then from a mathematical standpoint, if that's who you are, if you are like algebra, and this book is for you. Anyways, it's for me. Funny story. I held it up one time when I was explaining that this was my latest and greatest little wireless Bible here to some of the guys. We were on a conference call together. I held up one of the pages, and Cody Cochran, he says, the answer to that is 7, when I pointed out a formula similar to this one here. So that's just the kind of response that I would expect out of this. However, for a guy like me, I can take some of this algebra here. Some of it I have trouble doing, but I have to, you know, use Wikipedia and other things to figure out how to do this again. But the formulas come up right. All right, enough babble. Let's talk about the different antenna system types that we're dealing with when we're talking about MIMO. So the traditional antenna system is a single in, single out. That's what SISO stands for. So on one end of the link, we have a transmitter. On the other end of the link, we have a receiver. And then perhaps in a full duplex scenario, we have another transmitter over here. and another receiver over here in a time division duplex environment or in a half duplex environment. Will be transmitting towards the receiver in one moment, and then the next time interval will take and switch, and transmitter will turn on the end that was receiving, so on. So we see how that works, and so we have a number of different characteristics of that we have to look at when we're going to compare these. And as I'm going through my short little slide deck here, it's only a dozen slides or so. We'll get an idea of what's going on here. So the advent of the ASIC, actually, the analog processing chip, kind of really ushered in the business of multiple in or multiple out. Prior to that, all systems were SISO, and even in diversity systems in point-to-point microwave, it was really two SISO networks because there was antenna switching that went on. Receivers were switched in and out. When the main receiver was experiencing fading, then it switched to the standby or the alternate receiver, and then when the main link cleared up again, it switched back. And so it really wasn't MIMO, even though there were two antennas coming into a single microwave terminal, two different receivers. They weren't actually mixed. Today, that's not the case. Today we're using this single in, multiple out business. We can have one transmitter, and it can be received by two receivers that we have over here. So in this particular case, let's talk about licensed point-to-point first. We have a case where we have a transmitter on one end of the link, one terminal, and it's going to be received at the same time by both the main and there's the main antenna and the diverse antenna, and then it's brought together into one radio or shared. The data is shared between two radios, and so there is a form of MIMO that is going on here, and that is called single in, multiple out, or SIMO. The other place where SIMO has been used extensively is in uplink from first generation LTE, for example. In the uplink, if this would be the CPE at this end, this would be the base station at this end. And so we have CPE transmitting out of one antenna and being received by two antennas at the base station. This is also a form of SIMO, and we're going to talk about a little bit about maximal ratio receive combining and the business of bringing these two signals together and what, from an RF perspective, what they do. All right, multiple in, single out is far less common. Rarely do two transmitters end up being received by a single receiver. However, this is a form of MIMO, and so it isn't part of the mix. But by far the most common today is multiple in, multiple out. Right. So we have two transmitters at the base station, each transmitting different streams of data. We'll see what the differences are as we go along here, and being received by two receivers at the other end. And by some magic, the two streams are kept separate. Well, we're gonna investigate this magic that goes on, and you'll see how this all works. All right. So there's some principles of MIMO that are real important to get fixed in our in our thinking right off the bat. On the lower left here, we have a transmit stream, a transmit processing signal processing flow here. So bits coming in, symbols are mapped. They're converted to a QAM. We talked about that last week, about that process. If anybody wants to go over that, you could just listen to last month's Tech Talk with Dave. Or if you want to take and just send me an email, you'll see the email address at the end at marketing@mbsiwave.com, and we can go over how the quadrature amplitude modulated modulation works in here. But so let's skip past that for a minute. We have in the symbol mapping box, we have this modulation going on. Then we have the transmit processing, where we have filtering that goes on. We have up conversion that happens here. So we have mixing that occurs. We have then we get up to the operating frequency, whatever that is, 3 gigs, 5 gigs, whatever that happens to be, and off it goes on the air. When it's received at the other end, we have, of course, since we got one transmit stream, we have exactly the same signal at each receive antenna. Now, inside of this, in this, there's a couple of things that have to happen here that in order to take and decode this properly. One of them is that we need to be completely synchronized with the symbols that are being transmitted. So, in order to do that, we have our trusty GPS that's providing 1 pulse per second. At one end, we have our trusty GPS at the other end. Oops, GPS. Again, supplying that 1 pulse per second at this end. And so we have symbol sync. We have the transmitter and the receiver are locked together. That way we can take and when a symbol is transmitted from transmitted out of the sending end, when it's received, the symbol that's received and processed through this RF down conversion and filtering process that goes on here is indeed the same symbol that was transmitted. And so then the quality of the channel is estimated. This little process always happens at the receiver, where the output of the channel estimation is applied to an equalizer. So we have some just like in the old days, we had a stereo. We want to take and boost the bass or increase the treble, whatever it happens to be. Well, in the RF world, we want to do exactly the same thing because of the fact that we have this fading that's going on inside of the channel, right? So we have fades here. I'll explain this graph here in just a second. But we have fading that goes on. So the signal sometimes is up here and sometimes it's down here. And so this equalization, what it does is it compensates for that. Now, one of the things that you notice about this fading that goes on in the channel is that it is frequency and time dependent. So if I were to look at this in 3 dimensions, if this graph would have thickness, then I would see fades within the channel on certain frequencies, on certain OFDM carriers, if this were an OFDM system, and others would not be faded. And the sum of all of this ends up making the channel response look similar to this graph. So the job of the equalizer here, very important. In this particular case, this is what receiver number 1 might see here. So the red is going to be receiver number 1. The blue here is receiver number 2, and the MRC, the equalizer in the MRC, is going to take and mix these together so that we have the sum is going to be this blue. So rather than having a really deep fade that would go from let's say here to here, maybe this is going to be 30 dB, something like that, quite severe. MRC will then take and reduce that fade to, let's go here. It might be only 15 dB. I'll show you a graph in a minute that explains this. So this is the whole point of Mimo. One of the points of Mimo is to take and reduce the effect of sending a broadband signal through an RF channel from the transmitter to the base station to the receiver, or vice versa, and to minimize the effect of fading and other propagation anomalies that occur along the way. This is the point. So in this particular case, the things that are real important here is the fact that it has to be synchronization and calibration between the transmitter and the receiver. We'll talk about that in a minute. We'll talk about this calibration business in a minute as we move along in Mimo. But what I wanted to show here was the fact that in fact these the point of Mimo is to take and not increase the signal strength, but to decrease the amount of fade margin that we have to apply. We'll watch this in a minute. Okay. So let's move on to a Mimo system, a full 2-branch Mimo system. And let's talk about the components that we have within it. So just as we had in the single out, the single in, I should say, system, here now in a multiple in system, we have our symbol mapping. We have so here we have modulation that occurs. Then we apply the signal to both our streams. So this would be stream 0 and this would be stream 1 if we count them the way that most manufacturers do. What we do is within this spatial multiplexing box that we have here, very important. We're going to see in the next slide here what actually goes on inside of this box. We have a filter. We have a device that changes the carrier that's being applied to stream 1 compared to stream 0. So they're in fact they're opposites. This little gadget right here, this process that we have inside of the spatial multiplexing takes and makes the streams, the 2 streams are going to be different. Now the 2 streams could send the same data. That would be called Mimo A in the WiMAX days, and in Cambium's in the 450 equipment. Or we can have dual stream or Mimo B when we have different data being applied to that. That's the job of the symbol mapping. It would be to take and make sure that the symbols are transmitted properly on the 2 different streams. So let's not worry about the data just for a minute. We go through this process where we have our calibration, and we have our RF up conversion. We have filtering that goes on. That's what this is all about right here, because we don't want to be transmitting all kinds of harmonics and everything else of this mixing that goes on here. So virtually everybody's transmit streams look the same, and this is all inside right from the symbol mapping all the way through. This process is all generally in a software defined radio. It's definitely in an ASIC. It may be some of this may be hardware defined, some of it may be software defined depending on the manufacturer of the equipment and whether it's a system on chip or it's ASIC, but nevertheless the process is almost always the same. So we get the 2 antennas. And some manufacturers will take and transmit one on vertical and the other on horizontal, or maybe the minus 45 degrees or plus 45 degrees on a dual slant antenna, depending on that's typically the LTE standard. And so then we have our 2 streams then that are on the air in different polarizations. And so you'll notice that these are all 90 degrees apart. So 90 degrees apart is the opposite in as far as an electromagnetic wave is concerned. So that creates non-correlation between the 2 here and assists with this whole joint equalization process here again, which we have in the receive stream. So we're transmitted, we're on the air, off we go to the receiver. Incoming receive streams. Of course, now we got the same here. Let's assume that we're on dual slant antennas here. So this one is going to be minus 45 degrees, and this one is going to be plus 45 degrees. So there is some difference between the let me write that so you can know it's degrees. All right. So there's going to be some difference between the 2 streams here. In this uncorrelated state, rather, we have whatever the discrimination that we have between the 2 polarizations as differences in the stream. well, this assists in the process, but it's not all of the process. So in this receiver now, we have, again, we have some filtering that goes on. We have some demodulation that occurs, and we have again, channel estimation. We always have channel estimation, and we always have this symbol sync. So the transmitter is timed off of the GPS again, right? The 1 pulse per second is the clock, and here at the receiver we also have 1 pulse per second. So we have the second clock here to make sure that the symbols, that when you know, at a particular time and a particular symbol arrives at the receiver and it gets decoded, it gets turned into the same 2, 3, 4, 5, 6 bits, whatever happens to be, depending on the modulation, and then is applied again to this joint this equalization. It's called a joint equalization because whatever happens to one stream is applied in the same way to the other stream, so that when there's equalization is required on one stream, by this channel estimation here, this equalizer will apply the proper correction to the other stream. Then when the symbols are again demodulated here, and you notice here that the process of combining the streams, again, in the spatial multiplexing, we have exactly the opposite going on here. So this is actually what's the math is called a Fourier transform that happens here, and here it's an inverse Fourier transform, but that's, you know, what goes on is not important. What happens here is the fact that in stream 1 in the transmitter, we have exactly the opposite process occurring in stream 1 in the receiver. And then the output of all of this should equal the bit stream that comes in the input. That's the whole plan, right? Is to get it from one place to another. So why are we doing all this complexity? What's up with this? Well, all of these are operating on the same frequency, right? So we're using one channel. So what we're doing here is we are increasing our spectral efficiency because we are actually putting out a pair of bit streams over the air in the same channel at the same time, receiving that pair of bit streams over the air at the same time and decoding them, seeing what the difference is in between the two streams, and successfully sending a bit stream that would be 2 times or more, depending on filtering and modulation and other things. But essentially, I have 2 times the capacity here that I would have in a SISO environment. Plus, I have the advantage here of the Mimo streams interacting with each other over the air, and we'll see in a second here what that means. All right. So let's look at this space-time multiplexing or space-time coding. The algorithm itself, the code itself, is called Alamudi, right here. And so you see that sometimes in the spec sheet. That's what they're referring to. They're referring to this space-time coding. They're referring to this this carrier inverse function filter here that's applied to one of the 2 streams. The result of this is that if I was to take a receiver on the -45 slant, let's complete this drawing, -45, and this is +45 degrees, right? Antenna. On stream 0 in the -45 degree polarity, I have my symbols in order, 1, 2, 3, 4, as they're coming. On the other stream, on stream 1, I take and I transmit the second symbol first, the first symbol second, the fourth symbol next, the third symbol next. So you see I have an inversion here. I have I am not transmitting the same symbol at the same time, but I'm delaying them by whatever the symbol time is. For example, in LTE, this would be, whoops, this would be 103 microseconds, right? Every 103 microseconds, I'm transmitting a different symbol. So in my stream 0 and stream 1, I'm transmitting the same symbol in a different stream at a different time. And so this is called space-time coding, this whole process. And the flow chart here makes it real simple that you know, I've just got this this Z function here to the -1. So it's assuming that that Z is the filter Z is being applied to stream 0, and the filter Z to the -1, the inverse, is being applied to stream 2. And so that's right out of the symbol mapper. And so this is how this is all generated. Now, all the rest of the transmit streams are the same. I apply the same filters. I apply the same mixers and upconvert and transmit towards the other end. Inverse is absolutely true with let me just back up here. So here we have my Z to the -1 filter on stream 1 here. Well, look down here. I have Z to the Z to the -1 filter also here on stream 1 in my receiver. So the two are the two streams are in fact received together, and because of the application of this filter and the symbol sync and the channel equalization, I can take then and decode the two sets of symbols separately and recover the data from each of those. This is the magic of Mimo. So now I'm doubling my spectral efficiency, and I am reducing the required SNR for a particular error rate without requiring more power. This is a big deal, without requiring more power. Because in our world of frequency reuse now, with you know, more and more wireless systems on the air in the bands, we don't have you know, a lot of spectrum. In some bands are very, very tight. We have to do frequency reuse, and so we want to transmit less power. We want to take and decrease the range that we're going to allow CPE to connect to a base station, in order to take and increase the efficiency and increase the capacity, increase the data rate that we're going to transmit between you know, our base station and CPE and base station. So this is important to Mimo because it accomplishes this increase in performance without increasing the power that's required to do that. If we were doing a SISO system, the only way that we could decrease the fade margin that we have to build into the network would be to increase the transmit power. And so Mimo gets us past that obstacle. All right. So the effect in the channel, what does it really mean? All right, let's start here with my little channel response here. What we have is just simplified it here. We have one chain, and in fact, we know there's two. As the two sets of symbols are being transmitted, even though they're in the same frequency, and even though they are you know, within the same channel, the envelope of the channel, or the channel response, is very different for the two. So this is the whole point of the joint equalizer. We need to do that. This is what the channel in fact looks like. It is not you know, it'd be wonderful if a transmitter puts out you know, 1 watt, and at the receiver you're always going to receive, you know, exactly the same amount of power all the time. That does not happen. This happens where we have fading. We have other things that are occurring. We have fadings that occur on particular OFDM channels. We have fading that occurs actually in the streams, and they're different to each other because of the fact that the RF that's transmitted is different in the respect of the whole way Mimo works. So let's take an example here. If I have I want to have a error rate of 1 in 1,000, right? I want to maintain 1 in 1,000 error rate. If I'm using a SISO system here, m streams equals 1, right here. That's my blue line. It comes out here. In order to maintain that 10 to the minus third, or that 1 in 1,000 error rate, packet error rate, I need to have 30 dB of fade margin. That's huge, right? That's monstrous. We know that by the free space loss formula that I double my range every 6 dB. So this is double that I need to, or half that I need to half the range in order to take and maintain that on the SISO network. And we see that oftentimes. We'll take in the old days, single channel, single in, single out radio systems. If you connected the CPE up to a base station, for example, at near the bottom edge of performance, like let's say you got a 20 megahertz channel and you connect it up at neg 85, and you're going to flow 50 megabits or something across this channel. Everything works good when you first start off, and then a little while later, because of the fading that goes on, the customer starts to complain because there's times where they have outages. There's times where they can't decode that data, all sorts of trouble. All right, along comes Mimo now. Two-stream Mimo. Why is two-stream Mimo the workhorse here? Well, for the same error rate, if I follow my line across here, I'm now at, instead of 30 dB SNR, maybe I'm now at 17 dB SNR is required with 2 streams in order to maintain that 10 to the minus third error rate. Well, that's huge. I've taken virtually I've increased my range by 4 times by just simply going to a Mimo, or I've increased my penetration by 4 times. However you want to look at it, I've taken and improved my signal that is being passed back and forth between my base station and CPE and back again by this 12 or so dB, simply by going to 2-stream Mimo. Now, if I go to 4-stream Mimo, in this case, I will improve my fade margin required from 30 all the way down here to 12, or give or take. So let's say that's 11 dB right there. So now I've got 19 dB of improvement simply by going to 4-stream Mimo. So this is the reason that 2-stream Mimo is the workhorse, is that this right here is the biggest the biggest bang for the buck. I can do 2-stream Mimo all day long. 4-stream Mimo costs me double the transmit streams, double the receive streams, increases complexity, does other things. So 4-stream Mimo has not been that prevalent in the past, but it's coming. And so this is some of the improvements that are going to happen in the future here, is that we're going to go to 4-stream and more 8-stream Mimo. 8x8s and 4x4s are going to become real common. And so what we're doing here is we're decreasing the amount of fade margin that we require in order to pass our good old 1 in 1,000 frame error rate. This graph happens to be the graph for Qpsk. So if I go to QAM 64, all that happens here is that my x-axis here slides. It slides to the, in that case, it slides to the left. If I'm going to QAM 256, it slides to the left some more, but the shape of the graph stays the same. So my differences between 1-stream, 2-stream, and 4-stream and 8-stream stays the same no matter what the modulation level is. It's just the amount of fade margin that I need to support that particular modulation level increases. So this graph is pretty revolutionary in your understanding of Mimo. If you didn't understand what it did before, now you do. Also, you can see through all of this that if you have half of the MIMO chain not working, let's say, for example, you've got an antenna jumper that goes bad. So the left slant is working okay, but the right slant has high reflected power, high attenuation, and it's not working right. Well, we go back to the receiver may or may not be able to handle that, right? Let's the second chain here. Let me go back to one more. Whoops, come on. Yeah, sure. Easy for you to say, right? All right. Let's go back one more here. So this receive chain, it needs to have the channel estimation from both streams in order for the equalization to work properly. The symbol sync needs to work. If the symbols were missing from here, from my second stream, and I only had symbols from the first stream, my efficiency here of my MIMO receiver is impaired. So real important that we take and make sure that when we're running with a MIMO system, that we have proper connections to all of our antennas, both at the CPE and at the base station itself, or in the case of the point-to-point world, at the both parabolic antennas on either end, whatever it happens to be. We need to make sure that our connections are good, so that equalizer and that channel estimation algorithm, the CQI, works properly. All right. Now, MRC. So what I wanted, I've got this here, just so that we can see that I have the same relationship. It's just that depending on what the MIMO function is in this case, so we're talking about SIMO, right? A single in, multiple out in this particular case. So this would be the, for example, the first thing I thought about when doing this was the first generation fixed wireless LTE, a Cat 4 CPE that uses one transmit stream. So received at the base station, and we're applying this maximal ratio receive combining. So it's either MRC, or oftentimes in a spec sheet it might be called MRRC, but the process is the same. So our MRC gain over pure MIMO is about 6 dB. When we have multiple receivers, we have about 6 dB less fade margin required for the same error rate. So this is why in one of the questions that I used to get all the time when I would teach an LTE course was, I got 30 dB out of the base station, 30 dBm out of the base station, or 1 watt or even 10 watts out of the base station, but I've only got 23 dBm coming out of the CPE. How is that a balanced path? Well, it's balanced because we have some system gain that the MRC supplies, about 6 dB. And so ultimately, when I add up my power gain for the two and my 3 dB and my system gain of about 6 dB for the maximal ratio receive combining, I end up with about 9 dB gain in the uplink compared to the downlink. And so at my 30 out of the base station, 23 out of the CPE, I am actually 2 dB better in my uplink than I am in my downlink. And so what happens here is that automatic transmit power control, of course, takes over. ATPC is running in the CPE all the time. And so my transmit power of the CPE goes down because I have this gain in my base station receivers. And so anytime that I can reduce my transmit power and achieve the same results, it's really good for the network. It's really good for co-location. It's really good for frequency reuse. All right. So from a MIMO perspective, beamforming is right on its doorstep. So what's beamforming? What does it do? So beamforming will take this whole MIMO process one step further. And the channel estimation then that the receive stream does is then used for some other purposes. So we have here in the case of beamforming, we start off with two-stream Mimo in this particular example. We're going to apply beamforming to it. I can beamform with more streams if that's what I want to do. And there's really no limit here except for the complexity of what I want to take and provide in my base station. So each Mimo stream, remember that each Mimo stream has influence on the co-transmitted streams. The Mimo receiver provides channel estimation information back to the transmitter. We'll talk about that on the next slide. And then we just simply take, and instead of using one or two streams, we take and we can form this up. If you notice here, the transmit chain in this particular case is the same for both plain old Mimo and for beamforming. So if we have Mimo, then beamforming is really close by. So a couple of important things here. There's a word that we haven't been using typically, but you'll see that error every once in a while when you have a piece of equipment that's you know, the magic smoke has come out of or whatever. It might give you a calibration error. This calibration error or the calibration is important because the transmitters have to take and be able to test themselves in the beginning when they boot up. They test themselves and make sure that what they're doing lines up with what they want to transmit. At the receiver, the same thing occurs. That when the transmitter speaks, the receiver hears, and the filters, the equalizers, everything has to take and then be able to do within limits of you know particular limits. It's called calibration. If it fails any of these, if something's out of limit, like for example, if one stream is non-existent, for example, at the receiver, the CPE might report a calibration error in the log, but in fact, what it's telling you is that I don't see half the signal. So this calibration is an important function that goes on here, and it's one of the reasons why sometimes booting up a modern base station does take some time, is because it goes through this whole process during its boot up. So, so we need to have this. So we have the calibration that comes back from let's say we transmit downstream. The CPE will then take and estimate the channel, go through all that process, sends the information back to the base station. So typically, one thing that before we get to the next slide, I want to point out here is that typically beamforming is reciprocity based. What does that mean? Well, beamforming since we have to take and transmit a calibration signal and then process that calibration signal and send the results back to the other end, theoretically we should have to beamform with the CPE and we have to beamform with the base station. Well, it turns out statistically that we don't have to do that in order to increase our performance to the CPE. So what manufacturers do is they make the assumption that the uplink and the downlink look the same. If a particular type of equalization has to be applied to the uplink, or the downlink, I should say, then that same equalization is applied to the uplink, based on what the downlink is doing. And so the uplink and the downlink are considered similar. So when calibration occurs, the calibration signal is sent from the base station to the CPE. The CPE responds back, and the same variations to the signal that we need to do in order to accomplish this beamforming, which we'll see in a second here, is applied at both ends. So when we have uplink beamforming, that's all controlled by the base station itself. And so in the 450M, for example, we have two-stream Mimo in both directions. We have beamforming in both directions. and that's all calculated within the 450M access point. In LTE, we typically in fixed LTE, we've had downlink beamforming, but we haven't had uplink beamforming. Uplink is coming. Every manufacturer is going to have uplink beamforming, as well as carrier aggregation and all the other features, which we'll talk about some other time. But right now, I would just want to concentrate on this business of beamforming. All right. So the difference between plain old Mimo and beamforming itself is this precoder business right here. So the information after the symbols come out of the spatial multiplexer, the channel estimation back from the receiver at the other end, right, is fed into this precoder. So what essentially the CPE tells the precoder is that on stream 0, here's my SNR. On stream 1, here's my SNR. And so the base station will then take and adjust that in the precoder here, it will take and adjust that the equalization on one or the other channel. So adjust the filter. There's a filter that gets adjusted on one stream, or sometimes on both streams, but on one stream for sure. And then what that does is it changes the relationship between the two signals as they leave the antenna here. So in fact, what happens is that because this relationship changes, when I have a base station, so let's say this X is my base station, and I have a CPE. We'll make them some O's out here, just for simplicity's sake. The CPE number 1 up here, so we'll go 1, 2, and 3. CPE number 1 will say to the base station, my SNR is such and such on stream 0 and such on stream 1. The base station will then say, okay, when I'm talking to stream 1, it looks like I have to take and adjust stream 0 by so much phase. And when I do that, I change the relationship on my antenna, and I will actually increase the performance towards CPE number 1, decreasing the performance to CPEs 2 and 3. And so C2 and 3 go through the same process. It's called sounding. The whole process itself is called sounding. And so in this sounding process, in the base station itself, it remembers what the equalization had to be for CPE number 1, for CPE number 2, and CPE number 3. And it applies it the same every time. And then every now and again, sounding doesn't have to be continuous. Sounding can be every few minutes, as a matter of fact. And so the sounding occurs, again, at these long, for RF anyways, long intervals. And the equalization, the precoder settings then get adjusted for the CPE that are out there. Well, that's a little bit complex because every CPE will then have an entry in a table in the base station in order to provide the precoder settings for that particular CPE. So manufacturers do something else. They make groups out there. And so there is this precoder codebook that is part of the precoder database, for example. So if I go back to my CPEs out here, in this precoder codebook, any CPE that is out within maybe 10 or 15 degrees of each other out here, they will have one particular beamform setting, so one precode setting. The CPE that are here, might be a bunch of them, they will have a second precode setting, and the CPE that are down here will have a third precode setting. So there's a number of groups. Like in the 450M, for example, in 3 gigahertz, there are 5 groups possible. So I can divide up my 90-degree sector into 5 different groups, and then I apply the same precoder setting to all the CPE that appear in that group. And if there's no CPE in that group, well, then that precoder is never transmitted, right? Because there's nothing out there to talk to. So if for beamforming, if I had all my CPE grouped together in a small cluster, I would not be able to take advantage of the multiple groups, because as we're doing this precoder business now, if I go back to, whoops, let me go back here, I can have a number of different beamform groups here. So I'm going to transmit my two streams on each group, but I can have up to, oh, I don't know, current state of the art is 64 different Mimo feeds out of a 64 by 64 antenna. So I can have a number of these, and that just simply takes and defines how big this precoder code book is, how many CPE that I can talk to at one time. So if I have 5 groups or 6 or 7 groups or whatever I happen to have here, then my sector in the 450M's case is divided up into 90 degrees. In let's say in Telrad's case for their multi-user MIMO, it's divided up into the 65 degree antenna is divided up into these groups. And so depending on what the antenna is, depending on how many groups there are, goes to the efficiency that we can achieve inside of that channel. So the point of, let me back up, oops, back up. The point of all of this is that I can take and replicate my MIMO settings any number of times, right? As many times as I have dual ports on my antenna. So I can take then and if I had 3 groups here, I can theoretically achieve 3 times the capacity that I have here. So if I have 3 groups, here, that's 3 times of what I can achieve with one MIMO group. This is the point of beamforming, is now I can increase my spectral efficiency even more. I can take and apply more CPE out there at the same data rate, or I can take and increase my data rate some to CPE, but really my capacity is still limited by this MIMO pair that I have. So in this MIMO pair, if my channel is 20 megahertz wide and my efficiency for a single MIMO pair is like 5 bits per second per hertz, that means that I can do about 100 megabits. If I go to multi-user MIMO and apply this beamforming, then if I have, I don't know, 3 groups, then all of a sudden my initial capacity, rather than being 100 megabits, is now 300 megabits, give or take. There's something called implementation loss that goes in here. It's not exactly 3 times. It's going to be something less than 3 times, but it's going to be more than if I had just a single transmitter out there. That's the point of beamforming. All right. So our precoder is the big deal. This is the piece of software that gets written in software-defined radios. This is why the code is the operating system in the radio might be 70, 80 megabytes in size, compared to just a plain old MIMO radio might be only 20 or 30 megabytes in size for the firmware. In a system on chip, the system on chip then has these functions built into the chip, and then the operating system in the radio will then take and call on that function, the chip's capability, and then bring them together. So this is the essence of building this stuff. The essence of operating it, of course, is that the manufacturers are continually trying to take and get a little bit more efficient and do a little bit more with what they have in the equipment. And so that's why new versions of firmware come out, bugs get fixed, and features get added and whatnot, because of the fact that all of this is now possible, because beamforming might be built into the ASIC that's the system on chip that's driving the radio. In the case of software defined, then somebody sits down in the beginning and writes the software to make this go. All right. So in summary, we have our SIMO communication system. You transmit a single antenna and multiple receives. The two examples here are point-to-point spatial diversity and with fixed LTE uplink. The MIMO communication systems becoming far more prevalent. Wi-Fi 6 is MIMO, whereas Wi-Fi from 802.11n and back is not. It's SISO. So we're here. We're doing MIMO now in even in Wi-Fi. We're doing MIMO in access systems. We're doing MIMO all over the place. Space-time coding is the formula that allows us to take and put two streams on the air at the same time and be received and be able to be decoded by the other end on the same frequency at the same time. Pre-coding is used to transmit beamforming in MIMO. The channel estimation in MIMO system requires different training sequences for each antenna. The channels to each receive antenna are estimated separately. In case you were wondering about that, it's not one CQI that comes back from the CPE. If there's two streams, there's two CQI messages that come back from the CPE always. And so that will take then, and if there are four, then it's four messages that come back at 4-stream MIMO. So there's one for every channel. And then with OFDM systems, equalization becomes the big challenge here. So this becomes the complicated piece of firmware or software that's in the MIMO system, is that this is done also per subcarrier per data stream. So the electronics here gets to be, you know, quite complex. It's which is why these you know, ASICs have tens of thousands of transmitters or transistors, I should say, in them, is because they have all of these functions that are going on at the same time. And the last, but certainly not the least, let me talk about this just for 1 minute here. I put it at the end because it's real important. If you notice, when you're watching the logs in a system that boots up, oftentimes you'll see that the 1 pulse per second from the GPS is not only used for synchronization of the Ethernet, you know, the over-the-air frame size and those kind of things. It's deeper than that. The 1 pulse per second from the GPS is the source clock for the oscillators, for the mixers, for the filters, for the equalizers. They all use this 1 pulse per second stratum 1 signal from the sky in order to take and make sure that everybody's locked together. The transmitters and receivers are locked together, which is one of the reasons why that GPS is important now, and it's going to get more important as time goes along. So just last week we had our webinar on the Cambium, the TX switch, the CN Matrix TX switch. One of its big features is the fact that I bring my GPS into the switch, and then I send my Cambium sync up the tower on everything that I've got plugged into that switch. So the GPS, hugely important, and going to be more important for systems coming in the future. I hope this our hour's up. I can't believe it, but our hour is up, and I hope that I helped you take a little bit of the magic out of MIMO, understand a little bit more about what it is. I apologize. I lost track if I've got any questions or anything out there.
We do not have any questions right now, Dave,
okay.
But that session was awesome. And I know before we talked, you said 30 minutes, 45 tops, and here we are at the top of the hour.
Exactly.
And that's great. For the people that are still here, would you like to give them a little teaser on what to expect next month at Tech Talk?
Yeah, so next month, I've had a request from customers that we do a little bit of a technology update. So I'm going to take next month, and we're going to look at 60 gigahertz for part of the time. We're going to take a look at, since in Canada here now that most of you participated in the webinar, the tech talk the special tech talk that we had, where we talked about the Industry Canada point-to-point rates going down. Well, I'm going to talk about some of the features and some of the point-to-point technology that we have available to us now, that it doesn't cost a fortune to license the thing. And so quite looking forward to next month as we talk about technology. We talk about what's happening in 2021.
Exactly. So we're going to cover technology trends and then new technology features that have come available in 2021. So that one's going to be great. That will be June 16th, same time, 11 a.m. So looking forward to that one, Dave. And thank you for this session.
Well, thank you everybody for joining me, and have a great week, and hope to see you next month. Talk to you soon.